Hello, grade 12. Welcome back once again to this channel. Thank you for joining me today once again. This is Maths Paper 2, and today we're going to be focusing on statistics, grade 12 revision. Okay, like I said, we're going to be focusing on Mathematics Paper 2, statistics revision, and this is just revision, content revision of grade 12 statistics. As you can see on your screen, it's grade 12 data handling, and today we will be looking mainly at grade 12 statistics, right? So we'll look at different between univariate and bivariate data. We'll also check how to draw a scatter plot, and we'll also describe the correlation between any two sets of data in a scatter plot. We'll also focus on determining whether the correlation is linear, quadratic, or exponential. And we'll also look at how we can calculate the correlation coefficient, how we can draw an intuitive line of best fit, and also finding the equation of regression lines, and lastly look at using the regression lines to make prediction. I would really like to appreciate the Statistics South Africa FET study guide for making this content available. Okay, let's go. Okay, let's take a look at univariate and bivariate data. And really, after this lesson, I want to make sure that you really understand grade 12 statistics. So that you may be able to analyze or to solve any problem that they can give you in your exam. Okay, so all along you have been learning about univariate data, right? Maybe you might not know, but all along from grade 10 to grade 11, you have been learning about univariate data, right? So when you reach grade 12, they introduce you to what we call bivariate data, right? We can say univariate or unvariate, something like that. Univariate, let me call it univariate data. So this was a data that consisted of only a single variable, which mostly it was denoted by x, right? For example, that's why when they say calculate the mean, they would actually say x bar and all that, because it's a data that consists of a single variable. An example of that data is it's a mathematics test score. For example, they just give you this is grade 12 and this is grade 12A, and these are their math score for a specific test, right? So those are data that consists of a single variable, because we are just focusing on math tests only, so we are not focusing on anything. So those are the kind of data you have been learning all along from grade 10 and grade 11. It's called univariate or unvariate data. So this kind of data is analyzed by determining the measures of central tendency. We've seen you were asked to calculate the mean, mode, median, right? So those are the measures of central tendency that were used to actually analyze that kind of single variable data or univariate data. And you also saw that you were also made to or have to measure the measures of dispersion, determining the measures of dispersion, where you have to calculate the range, interquartile range, variance, and standard deviation, in order to just see how spread out your data values are towards the mean. And also you saw that with your univariate data or single variable data, you're also asked to draw bar graphs, histogram, frequency polygons, ogives, pie charts, broken line graphs, and box and whisker diagrams. And questions like how many learners in the physical sciences class are female, that were posed in unvariate data, because they were actually focusing on a specific set of data. Like I said, it's a single variable data that focuses on a specific item, such as the math test score, right? So that was unvariate or univariate data. Now, when you reach grade 12, they introduce you to a new kind of data, sort of like an advanced set of data, not really different to unvariate, but it's really unvariant. So the word bi, it means two, right? So it's two variable data. You understand? So then they call it bivariate data. So this is data that consists of what? Of two variables. And for example, we can say is the time spent studying mathematics. This is another variable. The time spent studying mathematics is a variable, and again the corresponding mathematics test marks to say, okay, let's look at the time this person spends while studying mathematics, and let's check their corresponding marks after studying for a specific time. So they want to measure two types of data, or two data sets that have different variables. You understand? So we call that bivariate data. So this data will be analyzed by identifying independent and dependent variable. To say from this example that I just shown you here, to say is the time spent on studying mathematics dependent on, or we can say is the corresponding math test marks dependent on the time the person will spend while studying mathematics. So you can see with bivariate data we can be able to check the relationship between to determine the relationship or the correlation that exists between those two variables, right? And again, also we can try to determine the strength of that relationship, right? Or that correlation. We mostly call it correlation other than relationship. The strength of that correlation between those two variables, to say if a person now is there a strong relationship between the time that we spend while studying and the marks that we'll get after studying for a specific time. So now you see that we start to determine the strength of that correlation between the two data sets here in grade 12. And also we can be able to answer questions like describe the relationship or the correlation between the time spent studying and the test scores. So you can now see that there's some sort of a correlation questions that can be posed from bivariate data, because we are just actually trying to compare two variables to say, is this influencing this? How strong is this variable influencing this? Or is there any sort of relationship between this variable and this variable, and all that? Okay. All right, like I said, we are really talking about bivariate data in grade 12, right? We are focusing on bivariate data. And like I said, with bivariate data, we can try to ask, to answer questions like, is there a correlation or a relationship between these two sets of data, between these two variables, right? So in order to answer that question, statisticians said no, we can use something called what? A scatter plot, right? We can use a scatter plot. So a scatter plot is simply a graph that will help you to see whether there is a correlation or a relationship between any set of two numeric data. So what do? You go and draw a scatter plot, and after drawing it, you'll be able to see whether there is a relationship or correlation between those two sets of data, right? So what does our scatter plot consist of? It has two axes, one for each variable. Obviously, we know in this example here, we have the age in the x-axis, and we have the mass in kilometers in the y-axis. So you can see we have two sets of variables there. So also each ordered pair of value is plotted as a point on a graph. For example, they'll just give you sort of like a table. Let me just draw it here. sort of like a table with two variables. They can say this is the time the person spent while studying maths, and these are the results they get. They can say time is in minutes, 30 minutes, 40 minutes, and 60 minutes. Maybe they can just give you 50, um, 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 58, then 75, right? So in order to sketch a scatter plot there, so the pair of the value 30 and 50, right? 30 and 50, we'll just plot it as a point in the graph. Somewhere there we just create our graph, then we go where there is 30, 30 where there is x, then 50 where there is y, then we just plot it as a point on our graph there. All right, so that's what it means. And also the x coordinate is the independent, as you know, independent variable is the x coordinate, and also the y coordinate is called the what? The dependent variable. So it depends on the other one, such as the results, right? Obviously, if you have the results and time, obviously on the independent, you'll put time. On the results, you'll put on the dependent, you'll put result, to just show that the results depend on the time that you'll spend while studying, to show that kind of correlation or relationship between those two sets of data. And an independent variable, as we know, is the variable that determines the value of another variable, right? So the dependent variable. So this variable can often be manipulated, such as the time you spend while studying is independent, and we can just manipulate it to see if you spend 30 minutes, 40 minutes, like that. But then the results, now the results, you can't manipulate the results, right? So that's the dependent variable whose value depend on the corresponding values of the domain or independent variable. So if there is a relationship between two variables, then you can say boldly that the variables are correlated. So you don't say there is a relationship, but you say the variables are what? Are correlated, if really there is a relationship. Okay, so let's now look at the types of correlation that can be there, or the types of relationship that can be there between two variable data. Okay, so as you can see, these are the types of correlation that we can have. We can have zero correlation, or what most students know as there is no correlation. No correlation. How do we know? From our scatter plot. Remember we said the scatter plot is used, we can see the relationship between two values, two variables, right? So from the scatter plot, you just see the points scattered everywhere to show that no, there's really no relationship between these two values. Each of them, they are doing their own thing. You know, when people are not together, we can't say there's a relationship when people are not together. But if they're just scattered all over, someone is there, someone is there, someone is there, it's really very hard to say there's a relationship between those people. So we call this zero correlation or no relationship. That is when the points are really scattered over the graph of the scatter plot. So an example showing this correlation is the marks on chemistry exam and the marks on art exam, right? For example, your marks on chemistry and your marks on art exam, those are two different subjects. There can't be correlation between these two marks, right? So there's no relationship. They don't influence each other in any way, right? So that's it. Also, types of fruits that people prefer and their shoe size. You can't say because someone is wearing a big shoe, they eat this type of fruits. No relationship. It does not make sense, right? So there's no correlation. Then number two, we have strong positive correlation. Strong positive correlation. For example, when people are together, holding each other, hugging each other, showing each other love and caring, you can say, no, there is a relationship, there is a strong relationship. They care for one another. Just like points here on your scatter plot, you just see them closely packed to each other to show that no. There is correlation, which is very strong. It's a strong positive correlation. How do we know that it's positive? Our graphs are moving that side. They're increasing towards the what? Towards the right hand side, top right hand side. Then we say there is a strong positive correlation, because when other variables are increasing, another variable is also increasing. That's where we say there's a strong correlation. But from your scatter plot, you can just see it by what you see there as they are moving like that. And an example of showing this, the number of pages in a newspaper and the mass of the newspaper. So the number of pages in the newspaper and the mass of the newspaper. We can see there's a strong relationship. If our newspaper has a greater mass, we can see no, there are more number of pages. So the relationship is there and is very strong, you see. So that's it. And the time spent studying and mathematics marks, right? Obviously, practice makes perfect. The more you practice, the more time you take while practicing, the better the marks you'll get on maths. So there's a strong positive correlation. 3, strong negative correlation. So now in this one, it's where your points show a band of slope downwards, right? Your slope is going downwards, other than this one, which was positive, which was going upward like this. But this one, they're like your points are showing a bend downwards on your on your scatter plot. So we say it's a strong negative correlation. As one variable is decreasing, the other variable are also decreasing. An example, the time spent watching TV and the test marks, or we can say the time spent playing, not watching TV mostly, but also watching TV. The time spent playing and test marks. There is a strong negative correlation. They don't influence each other positively. The more time you spend playing, not studying, busy watching TV, also your test marks will be decreasing. So there is a strong negative. It's negative because they are influencing each other badly. As one decreases, the other one is also decreasing. So there's a strong negative correlation. Then we also have a moderately positive correlation, right? A moderately positive correlation. You can see that they're increasing upwards, but they are sort of like scattered a bit moderately, not too far from each other, but they're just moderately pegged or clustered together like that. So we say it's a moderate positive correlation between them, right? So we also have a moderate negative correlation. It's where they're decreasing downwards like that, but you can see they're sort of like they have a distance a bit towards each other, but it's not too much. It's not like this one where there's really no correlation, scattered all over. But here it's just a bit scattered a bit, but then moving down the slope, we say moderate negative. Moderate negative correlation. So in many real life situations, scatter plots follow a pattern that are approximately linear, right? So this study you have seen, they were sort of like following linear and all that. But however, it might sometimes look as though there's no correlation between the variables, right? Whereas the points might look as if though they are randomly scattered over the plane. However, on a closer inspection, you may be able to recognize that no, there's some sort of a quadratic or exponential shape of the pattern of the points in any other pattern. So we have to also look at the quadratic relationship. Points can be forming sort of like a quadratic or an exponential relationship. Although in most cases you'll see them sort of forming a linear relationship, but they can also form a quadratic relationship. That is, this one for quadratic is when points are moving upwards from the left to the right and reaching a peak, sort of like, a quadratic graph. Reaching a peak, what following downwards movement like that. So we say there's a quadratic relationship or correlation. Sometimes for an exponential, they're sort of like forming an exponential graph. The points in this scatter plot for a curve from the left to the right and showing an exponential correlation. So we say there is an exponential correlation. Okay, let's take a look at this exercise. Let me just quickly give you an exercise that you can do. It says describe the relationship that exists between the variables in the scatter plot below A, B, C, D, E, F, G, H. So just give you some time, drop your answers on the chat, on the comment section, and I'll just respond to correct you if you are on the right line or not. All right. Okay, let's now move. We talked about the BIVARIATE data, and we say it's data of two variables, hence by from two, right? And then we say obviously between those two data they will be having some sort of a relationship or a correlation between them, right? Then I showed you the types of correlation that they may have. Now we are going to talk about the correlation coefficient. Now we want to determine to say if there is a relationship between these two sets of data. Now we have to also account to say what is the strength of that relationship and in which direction is that relationship going towards, right? So what is the strength and the direction? So in order to answer that question, we have to look at what is called the correlation coefficient, which is mostly denoted as small letter r, small letter r. So we say where there is a linear association, where a linear association exists between two variables, we say that the two variables correlate, right? So a commonly used statistical measure of association is called the correlation what? Correlation coefficient, which is its symbol is small letter r. So the correlation coefficient is the measurement, the measure of the strength. So it's the one that if we go and calculate it, we'll be able to account to say what is the strength of this thing. Is it strong? Is it weak? Is it moderate? Right? We use the correlation coefficient. It tells us about the strength and the direction of the linear relationship between the two variables. So with direction, we are saying, are they all going up? To say, like, is it positive or direction? Or are they going down? Is it negative? You see, so that is the direction. So you know that the correlation coefficient gives you two things, the strength and the direction of the linear correlation. The strength and the direction of the linear correlation. How does it give us? So there's a range of the correlation coefficient, right? It's between -1 and 1. So if X and Y have a strong positive correlation, then your R will be close to 1. It will be close to 1. Then we'll say, no, there's a strong positive correlation. So if your X and Y have a strong negative correlation, it will be close to what? To -1. Your R will be close to -1. Then we say, no. Here there is a strong negative. So you can see your R tells you the strength. Strong. When we say strong, is the strength. When we say positive or negative, when we say positive, they are all moving upward. When we say negative, points are sort of like moving downwards. So that is the direction, the strength and the direction. So if there is no linear correlation or there is a weak linear correlation, your R will be close to what? To 0. Your R will be close to 0. What if your R becomes 0? We can conclude that there is no relationship there is no correlation. That's it. Okay. All right, let's now talk about the line of best fit, right? So the line of best fit. So we are saying if there's a strong linear correlation between two aspects of the data, it may be possible to draw the line that best models the data, right? Because some of the points there might just be some sort of showing linear relationship, but if we are saying there's really a strong correlation between them, it might be possible to draw the line that best models the data, right? So this line is called what? The line of best fit, or what is mostly known as the regression line, or also called the least squares regression line. So this line is used for what? We use this line to predict or estimate the value of one variable given the value of the other variable. So to interpolate, what is also called to interpolate the things, sometimes to extrapolate. So we just use it to predict or estimate the value of just one variable if we're given the value of another variable. For example, if we have some sort of a data set, maybe we're given that this is a time we spent studying or practicing maths and the results that we get, right? So you might say 30 minutes, 35, 40, 45, then maybe 50 marks, 53, 58, and 62, roughly 62. So they can tell you, like, okay, if a student studies for 37 minutes, they can just tell you 37 minutes. Can you predict how much, or how much he can get in the maths test? What his results is? So we call that predicting or estimating the other variable, using the other variable, using what? The line of best fit. We use the line of best fit to do so. So the equation of the line of linear regression is y, very important, y equals to a plus bx, where y hat, it's just this one, y hat, and b is just the gradient of the line, and a is the cut on the y-axis, or the y-intercept. So that's all. So you just use your calculator to get those values of a, b, and b. So in this lesson, I won't cover how you're going to use your calculator, because this lesson is strictly conceptualizing of statistics content. I'm just helping you to understand this content so that you may be able to answer questions if you're given on the examination. So you use your calculator to calculate that line. We won't do an example to do so. You just use your calculator, calculate the line of best fit, and that's all. Right. Okay, great stuff. This marks the end of our lesson, our statistics conceptualization of content knowledge ends right here. Thank you very much for watching. Thank you for joining me. That's all from me, Ndondibuo. Goodbye.